Hello, everyone. So, welcome to the fifth, I believe, yeah, the fifth week of the Stefanich-Tannaka Seminar. And today we have Grigory Taroian from University of Toronto, and Grigory is going to be talking about almost rigid algebras. So, Grisha, please take it away.
Okay, thank you so much, and thank you for the opportunity to speak at the seminar. So, indeed, today we'll talk about almost rigid algebras. So it's section 2.2 in the paper, and I'm realizing that my handwriting is horrible. So this is a fairly technical portion of the paper, although maybe that could be said for most sections. But So I will try to first give some sort of conceptual outline what we're going to do, and then we'll prove this main theorem 2.2.5, which is sort of the core of the section. But yeah, before we do that, I want to just sort of explain the types of issues we're trying to tackle with this section. So I'm pretty sure that you discussed at great length the category Groth of Grothendieck pre-stable categories. So this is a two category of Grothendieck pre-stable categories. But the main issue that we need to resolve to have sort of robust formalism for this Tanaka duality is that the category Groth is not closed under small limits and co-limits. So we have this issue that Groth is not closed under small limits and co-limits. So as an example of why Groth is not closed under small limits, for example, Stefanich gives the following sort of almost classical example. You take categories of modules like this, and then you take the limit of this inverse system in PRL. So the limit PRL is the category of X-adequately complete ZX modules. And then we see that it's not abelian, so this limit doesn't exist in Groth. So limit not abelian, hence Groth does not have all small limits. And from this, you can deduce that it also doesn't have all small co-limits because you have this functor into PRL. And so because category Groth doesn't have all small limits, and this functor preserves all limits that exist, this functor can't have a left adjoint, so Groth doesn't have all small co-limits. Doesn't have.
Sorry, Grisha, can I ask a stupid question?
Definitely, I'm sure it's not stupid.
So you're saying it doesn't have a limit, it doesn't have small limits because the limit cannot be abelian, but aren't we in a stable infinity category world?
Sure,
So why is...
Sure, but I think the issue is that well, sorry, but I may be saying again, I may be saying something stupid, but I think at least the heart of this limit should be Groth in the abelian category, and it is
sorry,
not.
this is what you mean. So sorry, I was not. Thank you.
Yeah, no. It's a complete fair point. You can expect that maybe, like, in some derived sense, it still has a limit, but the issue is that sort of even on a classical level, this doesn't converge to anything reasonable.
Thank you.
Yeah. No, sorry. So it doesn't have a left adjoint. Yeah, and so Groth doesn't have small colimits. Okay. So that's sort of the problem that we're faced with. But then the point is that Groth does have colimits for diagrams with compact, almost compact. Well, I mean, there is like a somewhat subtle point about taking completions, but almost compact transition maps or transition functors. So again, the idea is that while the category Groth is not closed under all colimits, if you restrict to the class of colimits with on the like compact transition maps, then it would, like, the diagram would have a colimit, and in particular, the type of diagram we're very interested in because of our Tanaka duality setup is something like this. So you take some kind of monoidal, like Grothendieck pre-stable category, and then you're trying to calculate like the bar construction in the category of Grothendieck categories for two A modules M and N, and it would be nice, and in fact we would need an existence of such bar constructions or these like relative tensor products. So the realization of this bar construction should exist in Groth. And sort of the idea is that in this section we will prove some kind of technical result that shows that if A is almost rigid, whatever it means, then for like A modules M and N, the realization of this bar construction exists. Right. Well, I mean, we'll not exactly prove that. So this result will be proven in section 2.4, but we will prove something that is like very, very close to that, and in fact is like the main ingredient for proving that such geometric realizations of bar constructions exist. All right. Are there any questions so far? Okay. Then, if there are no questions, I will move on to sort of the talk proper. So this was like a trailer of what we're trying to do in this talk, and then it's going to be just like a grind of very, very technical arguments about existence of adjoins. So let me start by explaining the definition of almost rigid algebras. So the idea is that in like classical, even Tanaka duality of like Deligne and Milne or whoever, there is this concept of like a rigid monoidal category, which is something like very, very close to saying that It's like generated by dualizable objects, and I don't know. This is like a kind of category of finite dimensional representations that you reconstruct your group from. And then there is this. So for those of us, for the subset of us who were at this derived algebraic geometry reading group, there is an infinity categorical version of this notion of a rigid monoidal category, and we're trying to generalize this. So we want to generalize rigid monoidal categories of gate-scorer Rosenblum to the case of general monoidal two categories. So in the case of gate-scorer Rosenblum, the monoidal two category was the category PRL, and then the condition of rigidity was the condition that like the multiplication map admits a right adjoint. And now we'll just give basically the same definition, but we'll replace PRL with something more general. Okay, so let me give the following definition. So let's see, be a monoidal two category. Then an algebra object in C is called almost rigid if the following two conditions are satisfied. So the first one is that the multiplication map admits a right adjoint mu R like this, and the second condition is that the following commutative square is both horizontally and vertically right adjointable. Okay. And then
Wait,
this,
sorry to interrupt, Grisha.
yes,
I think in the right corner you mean A tensor A?
in the right corner, I mean A tensor 8. Thank you, yes. Otherwise, it wouldn't make much sense, right? Yeah, thank you. So, and finally, an almost rigid A is called rigid if this functor admits a right adjoint. Okay. Right. So, and as I was saying, in the case when C is PRL, we're specified to this notion of Gauge-Square Rosenblum. Okay, so now I can formulate the main theorem of this section. So theorem 2.2.5. So let C be a symmetric monoidal two-category. Let D be a left module over C. Let A be an almost rigid algebra in C. Let M be a left module over A in D. Then the following holds. So first, the action map is right adjointable. And second, if we take the square of action maps formed by any morphism between two modules, then it's also going to be right adjointable. So it's vertically right adjointable. Okay, so that's the main result, and like the idea is that we know that the multiplication map in this almost rigid algebra is right adjointable by definition, and then conceptually we should be able to bootstrap from this to the case of like the general module over this algebra. So, and let me let me formulate the following corollary of this result, which is used to prove that that transition maps in the completed bar construction are compact. So this is going to happen on the next talk, I presume. So the corollary is like this. So again, C as before, or rather C and D as before. So you have some sort of a monoidal two category. You have a module, and then A is an almost rigid algebra, and F from M to N is a module morphism over A in D. Then for the following commutative diagram, Oh, sorry. Just stop in my notes. There should be something else. Sorry. Okay, yeah, sorry. So for a diagram like this, so this is the multiplication map, this is the multiplication map. The square is horizontally right jointable. Okay. So now I think I can give the proof of this corollary, and then I will explain the outline of the proof of the main theorem, and then we'll try to prove the main theorem. So the idea is actually, I don't know, quite pleasant. We consider the following arrow category for D. So this is the arrow category. And then it is a left module over this. It is a left module over fun 1C. And then we have the constant arrow functor from C into its arrow category. So this is diagonal slash constant arrow. So this is a monoidal functor. And so by restriction of scalars, you have the action of C on this category. So now this square that we have here, let me denote it. So this square is just the action map for F in the category of arrows of D. So yeah, we just consider the category where objects are arrows. So the square becomes just an action map for a single object. And so now, now it's enough. To show that this multiplication map, this action map, admits a right adjoint. But this follows from the preceding theorem. So again, the idea is that you should be able to deduce some sort of rigidity properties for modules over an almost rigid algebra from just properties of the algebra. So in this case, we know that our A is almost rigid, and then we can actually like replace one module with another, but because like all modules sort of satisfy this rigidity property, doesn't matter, and we still get the right adjoint. Okay, so I don't know. Now I will give the proof outline, but before that, are there any questions? Sure. So now let me give you the proof outline. So as you can see, the theorem has two parts. The first part is proving that the action map is right adjointable. And the second part is proving that this square, which is comprised of two action maps and a morphism between modules, is vertically right adjointable. So let's start from the first part. They're actually somewhat independent of each other. So first, we will prove that mu m is right adjointable.
Sorry.
Yes.
Like, I have a question about the corollary. Sorry, I'm asking late. So you only used the first assertion of the theorem, right?
Yes.
Okay.
Yeah, I think so. Because we only need to use the fact that some like action map is right adjointable.
Okay.
Mm-hmm. Okay. So yeah, so the first part is to prove that mu m is right adjointable. So the way we're going to do this is like conceptually very simple to explain. So you know that for A, this is true. And then the first construction that you learn in homological algebra is that every module admits a free resolution. So we're just going to do that. We're going to construct like a free quote unquote resolution of every module over A. And then we're going to use the fact that taking geometric realizations and taking adjoints sort of play nicely with each other to see that there is a right adjoint for the actual map mu m. Of course, doing this in practice requires a certain amount of technical work. So let me write down this outline. So for the first thing that we're going to do, we will present mu m as a colimit of a semi-simplicial diagram in Z comprised of three modules. So the second part is that we will prove that provided right adjoints exist at every stage of the diagram, the right adjoint exists for the colimit And finally, we will deduce the existence of adjoints from almost rigidity A, existence of adjoints at each stage. So that's the plan for the first part, which is somewhat easier than the second part. And then for the second part, so for the second part, we want to prove right, vertical right adjointability of, let me actually copy the square that we want to investigate here. So we have the square. We want to prove that it is right, vertically right adjointable. So sort of the steps are more or less the same. We will reduce to a semi-simplicial diagram of 3 A modules. I don't know. I mean, then to analyze each stage, we will use the following trick. So we'll start from the following particular square for which we want to check that it is vertically right adjointable. And then we will deduce, prove that this is vertically right adjointable. And then deduce the general case from squares of the following form. So because our 3 resolutions are provided by the bar construction, that's sort of the stages of the resolution. So this is the action map at the nth stage of the bar resolution. And so this is just multiplying everything together, and then this is the action morphism. And then, so to analyze right adjointability of a square like this, will show that in fact you can realize this as an outer square of a square where you have something from the previous stage, so something like bar a m n minus 1, I think. Right, and then tensor a, and then bar a m n minus 1. And then for each of the squares like this, we'll either use the induction or the previous case to conclude that they're right adjointable, and so the outer square will also be right adjointable. Okay, so I realize that maybe even this overview is somewhat too technical, but let me ask you again, do you have any questions? Okay, right. Okay, so if there are no questions, then let me move on to sort of the technical core of the argument, which I would actually explain very poorly because I don't know. It relies on like previous results of Stefanich, and I didn't really want to go into the depths of like proving these results, even especially because they seem somewhat natural, and like you would just assume that this is true. So, but I mean, if I don't know, maybe we can read their proofs later if there is like a burning desire to learn more about presentable and categories and stuff. So, okay, interplay of colimits and adjointability. So again, the technical core of this argument is that we should be able to reduce the general case to sort of the case of free modules. The way we should be able to do that is that we should have statements of the following type. If you have like right adjoints for every stage of your colimit, then you have a right adjoint for the colimit map. And sort of the following three lemmas are precisely the statement of the sort. They will provide us with some conditions under which we can conclude existence of right adjoints for the colimit from existence of right adjoints on the stages of the colimit. So we have the following lemma, which is 2.7 in the text. So let's see B2 category. Let f from x to y be a morphism in C, presented as a colimit in the arrow category. So we have like a diagram f alpha x alpha to y alpha that presents this as a colimit, such that this colimit is preserved by the evaluation functors. So it means that the colimit of x alphas will be x and the colimit of y alphas will be y. And
so the sources and targets, right?
Yeah.
Right.
Yeah.
Okay.
I mean,
Thanks.
they're called evaluation functors simply because, well, if you present this as the category of functors from 1 to C, then this is going to be like an evaluation at 0 and evaluation at 1.
Right. Right. Thanks.
Yeah. No, I was actually confused about this name, but then, yeah, I realized that this was all very simple. So this is a very good question. Then assume that each square of the following diagram, of the following form is vertically right adjointable. So this is a square which is formed by the limit map and a map at each stage. Then we can conclude two things. So F is right adjointable. And for each alpha, a square like this is vertically right adjointable.
But Grisha, I have a question.
Yes.
Wait, so the assumption is, I think in assumption you mean like the square associated to every transition, I guess, for the assumption.
Right. Yeah. Otherwise, it wouldn't make any sense, right? Because you would basically be assuming part 1. Yeah. Sorry about this. And thank you for calling this out. Yeah. Of course, it's yeah. So this is like the transition map. Whatever. I'll complete the. Yeah. Sorry. Of course. Yeah. So yeah, we just want to deduce that the colimit map is right adjointable, provided that like every stage of the colimit is right adjointable. Thank you. And then so like a dual or converse statement to this is that if you have a square like this, such that it is vertically right adjointable, then for every square like this, so here we also assume that f prime is presented as some sort of colimit. This is vertically right adjointable. Sorry, what am I saying? Yes. So if no, sorry. If any square of this form is vertically right adjointable, then the original square is vertically right adjointable. So you can do this for sort of natural transformations between colimit diagrams, and then you can deduce from this that the colimits are vertically right adjointable.
Yeah, sorry to interrupt again. Sorry, but do you mean for the first square, it's like just x prime in the right-hand side, like x prime to y prime, or is it x prime alpha to y prime alpha?
No, I think
because you said it's like the converse of the first statement, right? So shouldn't it be
right.
like just
Right? Yeah. I think you're right. Yeah. Yeah. but then right. Yeah. 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 Just this. Okay. Yeah. Sorry about this confusion, but yeah, that's the statement. Okay. So I'm actually not going to prove this. So this is demonstrated in this paper of Stefanich about presentable N categories. Source Stefanich presentable infinity N categories. Okay. So now let me also formulate the next lemma, which is sort of a similar flavor, but now it's about colimits in the category of squares. So this is 2.2.8 in the text. So assume that you have a square like this. So assume that no, just we can just assume that sigma is a colimit in the category of squares of sigma alpha, where like sigma alpha are the same things but with alphas everywhere. So in fun 1 cross 1 C. So C as before. So it's two category. And then
Grisha, sorry to interrupt.
yes.
F is a map from X to Y, right? I think there's a typo. It looks like
Yeah.
alpha.
There should be just Y. Yeah. I erased alpha for X, but forgot to erase it for Y. Yes. So we assume that this is a colimit of sigma alphas, and assume that the following holds. So first, sigma is vertically right adjointable. Sorry, sigma alpha is vertically right adjointable for every alpha. For each transition, the resulting squares of sources and targets are vertically right adjointable. And finally, sorry, this is just the condition. Then sigma is vertically right adjointable. Again, this seems like a completely believable statement, and this is demonstrated in Stefanich sheaves. What is it called? Sheaves of one categories. Sheaves oh no, sorry. Higher shift here. Which is supposed to be a sort of, I don't know, rework of the first volume of the Explorer Rosenblum. Okay. So again, so this is again some sort of lemma that says that if you have right adjoints every stage of the column, and you have the right adjoint of the column it's in diagram, and then final lemma of the sort is lemma 2.2.9 that says that if C is a two category, and you have a commutative square like this, suppose that F is a geometric realization, such that after applying evaluation functors, the diagram splits, and assume the following conditions. So G and G prime admit right adjoints, and for each n, the following diagrams are right adjointable. So this diagram, and then a similar diagram where you map into X prime and Y prime. Are very, oh, sorry, not very, horizontally right adjointable. Then sigma is horizontally right adjointable. Okay, so this statement would be extremely relevant for this type of bar construction argument, because there we're actually presenting something as a diagram which is like a simplicial diagram which splits after you apply like the source and target functors. Okay, so we can actually prove this result since the proof is self-contained. So let's denote by HN maps like this. So this is the canonical map in the colimit. Canonical maps. Then denote by eta this kind of Bach-Chevalier transformation. then our goal is to prove that eta is an equivalence. So I didn't actually introduce the notion of like either left or right jointability, vertical or horizontal jointability of squares. Somehow I presume that this was, I presume that this was done before. And then, so the idea is that for a square to be either horizontally or vertically adjointable is equivalent to assuming that, well, first of all, like either the vertical or horizontal maps are supposed to have right adjoins, but moreover, the natural Baxter-Valea transformation is supposed to be an equivalence. And that's sort of what we're trying to establish here, because we already know that right adjoins exist. That's something that we have to assume to even start. But then if they do exist, we need to prove that this Baxter-Valea transformation is an equivalence, and we're going to do this right now. Okay. So consider the following diagram. So this is Fn, Yn, Hn, Y, G prime, Y prime, F prime. Yeah. So by assumption, 2 out of 3 squares in this diagram are horizontally right adjointable. So we want to show, let me first indicate which are. So we know that this one is horizontally right adjointable by assumption, and also this one is. And we want to show that, use some other color. Want to show that this is okay, so we know that eta becomes an equivalence after composing with H and R, simply because, well, you have eta, and then by naturality, after composing with H and R, it will become like the Baxter-Valea transformation for the red square. And so consequently, it means that it remains an equivalence after you compose it first with H and R and then with Hn, because it was already an equivalence. And so now we just use the fact that this diagram is split to conclude that because Hn, Hnr, eta is an equivalence, consequently, eta is also an equivalence. Okay, yeah, so that's the proof. I don't know. Are there any questions about any of these three lemmas? Because the next stop is proving the theorem. Okay. So if there are no questions, then let's move on to the final part of my talk, where I will actually prove this theorem about the existence of adjoints. So the first part is proving adjointability of the action map. So as promised, we start from taking this action map μm, and this map can be presented by a geometric realization of the bar construction. So this bar construction is the simplicial object in D, and defined in the most standard way possible. You just take at stage n, you just take n copies of n plus 1 copies of A, and then you tensor it with M. Okay. So that's the bar construction, and then of course you can present the action map as this kind of tensor product of bar A M dot into M, and then you take the full limit, and then this presents mu M. So this is mu M dot. Then after you take the geometric realization, you get A tensor M into M. Okay. Right. So then we observe that by, I don't know, homotopy cofinality of delta inch inside of delta, you can, instead of considering the full bar construction, you can consider the semi-simplicial version underline bar. So this is done, I think, mainly because we want to explicitly verify certain adjointability properties for the structure maps in this bar construction, and kind of we don't want to deal with degeneracy, so we're just going to deal only with face maps. And that's, I think, the main reason why he passes from the simplicial version to the semi-simplicial version.
Grisha,
yes.
Could you please go up a bit? I had a question.
Yes.
A bit. So you're saying, yeah, that's about it. So the map, like a, could you go down?
Yes.
So this map, like a tensor bar a m dot that goes to M. Okay,
Yeah.
okay. Oh, my bad. Okay. Wait.
Yeah, no. I mean, it's just you present M as like this bar resolution, and then
Right. Okay. Thanks.
yeah. Okay, yeah, so by this, so by one of the previous lemmas, let me tell you exactly which one. Yeah, so by two, by lemma 2.2.7, were reduced to proving that for any p from n to n plus 1, the following square is vertically right adjointable. Oh, sorry, what? Yeah. This is mu n. This is bar a m n. This is mu n plus 1 bar m plus 1. Then this is bar.
Wait, sorry, I'm a bit confused. Like,
Yeah.
so this mu
Yeah.
n plus one, this goes to bar a n plus one because
Yeah.
above you define it like as going to m, I guess. Like if you go above
Sure. Yeah. So, but
mu n,
that's kind of a different type
oh,
of. Well, I mean, I think here you just multiply like a and the first term in the stage of the bar complex.
okay.
I think Stefanich doesn't even introduce like the notation for these maps,
Yeah,
nor
it's a bit
does he
confusing.
explain what these maps do, but I think that's what they do.
Okay, thanks.
So I think here you just multiply a and like this, and then whatever else is happening. Okay. So yeah, so we need to show that this square is vertically right adjointable. And the way we're going to do this is that we separate two cases. So one case is when, so obviously, phi is one of the face maps, and then you have two situations. Phi is di for I greater than 0. And so in this case, the following argument works. You take the following square, mu identity, and then you can tensor this square with the square of the following form. So this is n. This is n plus 1, or maybe it's something like n plus 2, n plus 1. Then have this thing here. So this is just the identity. This is again bar phi. And so because this square because mu is right adjointable, it follows that this square is vertically right adjointable, and then after you tensor it with anything else, the resulting square is again vertically right adjointable. Sorry, and that I said some nonsense. This square is vertically right adjointable again for is via array because mu is array. So when you tensor them, you get the vertically right adjointable square. Okay, so that's the case when I is greater than 0, and then the second case is when phi is the zeros phase map, and then in this case the resulting square, the square for G naught is obtained from the square in the definition of almost rigidity. So let me write the square again. From the square in the definition. So you take A tensor A, tensor A tensor A tensor A, multiplications, multiplication times the identity times the multiplication, and then you just take the square and you tensor it with A tensor power n tensor n. So because the square is right adjointable, vertically right adjointable by assumption, the resulting square will again be vertically right adjointable, and so we proved one in the theorem is proved. Okay. So that was part 1, and then for part 2, we sort of do all the same things, but it's a bit more complicated. Okay, so the second part is proving vertical right adjointability of the action square. And by the action square, I mean that you take two modules, you take a morphism between them, and then take a morphism between them, and then you want to prove that that the resulting square is right adjointable. I'm just trying to see if I'm writing it wrong here. Right, no, yeah, writing it wrong. There's too many A's here. A tensor M, A tensor M, M. Yeah. So we want to prove that the square is vertically right adjointable. And so to do this, again, the idea is that we should be able to do some sort of bar resolution to reduce this to the free case, and in the free case we should be able to use almost rigidity of A to conclude. So let me start from the following, consider the following special case. So this is exactly the case of sort of free modules. You have a square like this, A tensor M, A tensor M, M. So this is just proving something for like the structure map, defining the module structure, or proving something for like the pair of free module, like I don't know, any module in the free module, generated by this module. So yeah, so here we have identity A tensor mu M, mu A tensor identity M. We want to prove that the square is vertically rate adjointable. So to do this, we can just apply the argument to yeah, sorry. Yeah, so to prove this statement, we can just observe that this follows from almost rigidity of A, and then so how are we going to do this? So we pass to the bar resolution. Then we use lemma 2.2.8, and then use almost rigidity of A for each stage. So now we need to deduce from the special case the general case of an arbitrary pair of modules. So the general case proceeds by induction on M. So we're going to consider the following things. So we'll consider A tensor bar A M N mu N plus 1 bar E M plus 1, and then we will consider the corresponding map that goes through the co-limit and into the target module M. So this is identity A tensor F plus 1. So the base case n equal to 0 is the one treated above. And then for the inductive step, we can just observe that. For the inductive step, we can consider a diagram like this. So here we replaced both M and N with their respective bar resolutions. Oops. And then A tensor N. And so this thing is vertically right adjointable by the preliminary case, because this is the case where you have like a free module mapping into the module that it's generated by. Then and like originally we wanted to show that this square is vertically right adjointable, but as we saw before in the proof of this lemma 2.29, like the one right here, it's enough to sort of deduce that 2 out of 3 squares are vertically right adjointable to deduce that the third square is vertically right adjointable. So we want to deduce it for the blue square. It would be enough to deduce it for the top square. But for the top square, we observe that again, this is sort of the case that we treated before, because the following is true. So for the top square, it's enough to prove that this works for free modules A ones the form A tensor M prime and A tensor N prime, and F is of the form identity tensor F prime for some F prime from M prime to N prime. And so in that case, the proof just follows by taking this kind of multiplication square and tensoring it with this square. Oops. Okay, and so because because this square is vertically right adjointable. And we can assume that this square is vertically right adjointable. Their tensor product will be vertically right adjointable again, which would demonstrate that the top square here is vertically right adjointable. And so the larger square is also vertically right adjointable. Okay, so that's the proof. I'm sorry that it's such a mess, but I don't know. To be honest, kind of difficult, or at least for me, it's difficult to like find a nicer way to present this very technical result. Okay. Are there any questions?
Yeah, so let's thank our speaker first, and then we'll be open to questions, I believe. All right, so we are open to questions. And just to let everyone know, there's also a post-recording session. If you don't want to ask your question now, we could talk after recording, after the recording's closed. Cool. So if there are no more recording questions, let's thank our speaker again, and then we'll move to the post-recording session. Thanks again.